Warm welcome to day 2 of International Conference on Intelligent and Innovative Technologies in Computing, Electrical and Electronics, organized by the Department of ICIIB and MIT. On behalf of the organizing committee, I extend a warm welcome to our keynote speaker, Dr. Navakanta Bhat, Dean, Division of Interdisciplinary Sciences and Professor, Center of Nanoscience and Engineering, Indian Institute of Science, Bangalore. I extend a warm welcome to our Additional Director, Dr. S.Y. Kulkarni sir. A warm welcome to Dr. M.S. Suresh, a former Principal and Dean. Welcome to all the delegates, participants, students, HODs, and my dear colleagues. It's my privilege to introduce Dr. Navakanta Bhat to the audience. Please bear with me. It's a illustrious biodata, so I take some time to read this out. Dr. Navakanta Bhat received his BE in Electronics and Communication from SJCE Mysore, MTech in Microelectronics from IIT Bombay, PhD in Electrical Engineering from Stanford University. He has worked at Motorola's Networking and Computing Systems Group under Advanced Products R&D Lab in Austin. He is an elected fellow of IEEE, INAE, IISc, INSc and NASI. He has received the Young Engineer Award from Indian National Academy of Engineering, Swarna Jayanti Fellowship from the Department of Science and Technology, Professor Satish Dhawan Award from the Government of Karnataka. He is also the recipient of IBM Faculty Award 2007 and Outstanding Research Investigator from DAE. For his translational research work, he has received Dr. Abdul Kalam Technology Innovation National Fellowship, Dr. Rustum Choksi Award for Excellence in Engineering Research, Nina Saxena Technology Excellence Award, NASI Reliance Industries Platinum Jubilee Award and BIRAC Innovator Award, Distinguished Alumnus Award IIT Bombay. He has also received the prestigious Infosys Prize for his contributions in engineering and computer science category and Yashraj Bharti Samman for innovation in healthcare. He was a member of Board of Governors of IEEE Electron Devices Society EDS and also the Vice President of Educational Activities IEEE EDS. He was the chair of IEEE EDS Nanotechnology Technical Committee, editor of IEEE Transaction on Electronic Devices, and the chief editor of IEEE TED Special Issue on 2D Materials for Electronic, Optoelectronic, and Sensors. He is also a member of Committee of Semiconductors of International Union of Pure and Applied Physics. He was the founding chair of IEEE Electronic Devices and Solid State Circuit Society, Bangalore chapter, which was recognized as the outstanding chapter. Along with this, he is also the founder and promoter of a startup company, Path Shodh Healthcare Private Limited. Based on his group's research in biosensors, Path Shodh has developed the first of its kind multi-analyte point-of-care diagnostic device for multiple chronic diseases, including diabetes and its complications, anemia, malnutrition, kidney and liver diseases, and COVID-19 antibodies. For this technology, Path Shodh has received multiple recognitions like CII Industrial Innovation Award for the Most Promising Startup 2017, Federation of Indian Chambers of Commerce and Industry Healthcare Excellence Award for the Best Startup of the Year, Design Impact Award for Society Change by Titan. We are indeed honored to have you here, sir. I now request the dignitaries to honor our keynote speaker, Dr. Navakanta Bhat. Now I request Sir to take over the session.
Very good morning to all of you. It's indeed a pleasure to be here and interact with you. So what I'll do in the next 50 minutes or so is walk you through the amazing technological revolution that we have witnessed in the last few decades, and what are the challenges that are that need to be solved going forward, and the opportunities thereof. Right? Mostly the students who are out here. Things are getting more and more exciting, right? This is the best time to be, starting your careers, right? So, I hope that you will take that message from this talk. I've titled this talk as sensor scaling. I understand there is also online audience, so let me use the pointer from here. I think that would be better, so that they would be able to see this as well. So, this is also an IEEE EDS distinguished lecture, and I've used that emblem that was created last year to commemorate 75th birthday of transistor. Okay. In fact, last year all over the world, many IEEE chapters had a lot of cake cutting, to celebrate this birthday. In fact, in one of the premier international conference which happens, every year in the US in San Francisco, where most of the top technologies get showcased. One of the panel discussion was transistor 75 years, is it time to retire? Right. It turns out it's still very young, it's not a time to retire. Okay. But I would like to tell you a little bit about some area that we have sort of ignored, that is to do with sensor scaling, right? So that is the intent of this talk. Again, given the diversity of audience, I have structured it such that there's a lot of basic stuff, but I think it would be exciting, hopefully, but also touch upon some advanced concepts, right? So, many students and collaborators have contributed to the work that I'm going to present. And also, we have been fortunate to have funding support from many agencies, right? So, very good point. This is just to sort of illustrate that the first transistor which was invented in Bell Labs was PNP transistor. Okay, right. I mean, and also it's a bipolar junction transistor, if you see that. Although today's technology is really CMOS technology, which is essentially field effect transistor based technology. So this is sort of remembering the birth. Right, so that's why that PNP transistor was chosen as a logo to celebrate this occasion, right? Yeah. So, as I said, if you look up the IEEE side, there's a lot of interesting stories about this. For students, I think you should really look up this. So the outline of my talk is the electronics, the past and the present, where we are. How have we managed the scaling and the scale, right? And also, how have we managed the diversity of the blocks that we are putting together on a chip today? And then what is the emerging electronics, the bigger picture going forward, and the so-called smartness that we need in addition to intelligence. Often you see that this person is street smart, right? It may not be the intelligent, but he or she is street smart, right? There is different connotation for intelligence and smartness, right? So we also need to get smartness along with the intelligence in our systems, right? Okay. Again, before the birth of the transistor, PNP transistor, which was in 1947. That is when we got our independence, right? So that's when electronics also got its independence from the vacuum tube era, right? Because prior to that, all electronics, it's not that we didn't have electronics, we had a lot of electronics. We even had computers. But computers were as big as this room, and they were very rudimentary. This is one of those ENIAC in 1945. It had 18,000 vacuum tubes, it weighed 30 tons. Your mobile phone computer is more powerful than that today, and it consumed 200 kilowatts, right? So the biggest transformation came in 1947 by the invention of semiconductor transistor. That was a PNP transistor that I showed you in Bell Labs, and subsequently in 1958 by integrated circuit chip, IC chip what we call, by Jack Kilby in Texas Instruments. In fact, that's why both these inventions, the people who invented, Jack Kilby for 1958 invention and Bardeen, Brattain and Shockley, they got Nobel Prize in physics. Rarely Nobel Prizes are given to technology fields, right? This is just to tell you the importance of these technologies that have changed the way we live today, okay? And then the biggest, another biggest important thing that happened was really computer on a chip. That was Intel 4004 in 1971, about 2000 transistor, only, you know, a 1 watt power consumption compared to 200 kilowatt power consumption that was there, okay? And it was on a 10 micrometer technology, right? That is what we used to call then microelectronics era, because each transistor was measured in micrometer dimension. And then technology matured, we transitioned into what is called a 3D transistors, which are called FinFETs today, multi-core processors. You know, today each processor that you have many cores, and each chip has more than billion transistors today, easily more than billion transistors, right? And today we are also talking of 3D SoC, systems on chips. They're not just digital, they have FPGAs, they have RF, analog, everything embedded, including programmability, such as this Xilinx chip that I'm showing you here, which is on a 7 nanometer 3D SoC technology, close to 50 billion transistors, right? So this is amazing, amazing thing that we have done. You know, that is why electronics is the only industry. The best time to buy any product is always tomorrow, right? Because you get a better product at a lower cost, right? It is unparalleled compared to any other industries, right? Now, so the reason why we have done this is we have miniaturized. This is very important thing to remember. From what I showed you earlier, so-called 10 micron transistors, which is microelectronics, today we are building transistors which are less than 10 nanometers. That is what we call nanoelectronics era today. In other words, dimension scaling which is 3 orders of magnitude. Not just that. We have also started to cram more and more transistors on chip. Back in 4004 day, which was small scale integration, we had about few thousand transistors. As I showed you, 4004 had 2000 transistors. Today we have billions of transistors. That's an order of 7 orders. Combine this 7 and 3, this is 10 orders of scale, which is uncomparable compared to any industry. You know, that is the secret sauce of this industry, right? You miniaturize the transistor, which is a building block of your chip, put as many of them as possible on a single chip, and that gives you amazing functionality at a lower cost, right? So not just that, we have also been able to figure out to design such a complex chip. I mean, you have designed your breadboard circuits, few components. Imagine a designer's fate if he or she were to design a chip with 10 billion transistors. It's even possible to remember which transistor will go where. Impossible. And this revolution came now because of something called CAD, computer aided design, right? That is another revolution. Just imagine, it's a very, very interdisciplinary, industry. You have chemistry, physics, material scientists, electrical engineer, computer sciences, everybody coming together and making this possible, right? And because of this, you have these tools today that are available. You come up with an idea, you use these tools, come up with your physical layout of your chip, send it to your foundry, and invariably you get first time success, right? That also shows you the maturity of these CAD tools, right? There are many, many things that have happened. And maturity of the technology also. 10 billion transistors, if 1 or 2 transistors don't work, your chip doesn't work. Right? Remember that, right? That is the kind of, and today even chip design has become like writing a software. We will not really discuss that part here. So what has really happened is this is a triad that has fueled this innovation and growth. Okay, and this triad has 3 components: computer-aided design tools, which enable us to design the chips, and we build advanced chips, which of course help us create advanced computers such as mainframe, supercomputers, because to run advanced CAD tools you also need powerful computers as well, right? Otherwise it becomes impossible to, this is kind of a positive feedback cycle which has enabled this. We are building these silicon chips, this has become routine for us, but there are a lot of problems. To run these chips, they are consuming a lot of power. Today's data centers, such as Google's data center, you do a query on your mobile, really it goes to the cloud and fetches the information for you. The data centers are really hogging the power. It's expected that today we are already consuming, for electronics data center, more than 10% of global energy needs, and it's going to increase to 50% if we do business as usual, right? Because while digital technology has been amazing, digital technology is also not efficient. These chips consume power, mainframes and supercomputers consume powers in kilowatts and megawatts. Compare that with the brain. Oh, there is an echo coming there. Yeah. We have a supercomputer within us, right? We do a lot of things more efficiently than computer, especially pattern matching, recognizing a face. It's a hard task for computers. And what is the power consumed by the brain? At the maximum power consumed, only 10 watts. Only 10 watts. And we do an amazing complex jobs. And the reason for that, firstly, the building blocks of the brain are what are called neurons. They are analog in nature, not like transistors which are digital in nature, right? I mean, we are using transistor as a digital building block. Transistor can also be used as an analog building block. That's a different story. But we really have to start thinking about what is called a brain-inspired computing. So that is emerging as a new paradigm going forward, right? It doesn't mean that brain-inspired computing will replace the digital computing, right? I mean, often people get so excited that they say, oh, this is irrelevant now. This is very important. The brain-inspired computing chips will come as accelerators on your systems. The tasks which need a lot of computations, which are, image processing as an example, and neural network based computations, all these require computing and manipulating huge matrices, right? That is where, this technology becomes very important. So that is one message I wanted to give you. So this is an emerging area, what is called a brain-inspired computing, and it is just growing. It is in a very, very nascent stage. You will see huge, growth in this area in the next 2 to 3 decades, right? Remember that. Now, that is not the only thing. I think I probably have skipped this one slide here. Just 1 minute, if I can get that. Yeah, so I had hidden that slide. There's one more very interesting thing comes up. Just 4 or 5 days ago, you probably heard that there is what is called a National Quantum Computation Initiative. Okay, so this is another very interesting area that is emerging. In terms of how do we build systems going forward, right? Going forward, the systems that we will be building will really be compute systems which are very heterogeneous. They will of course use a lot of bits. That is what we have been doing all along. They will also have a lot of not really biological neurons. We still haven't figured out how to use them in our systems, but neuron-like computational elements. That is what I meant by brain-inspired computation. And the quantum computing components also, right? So that is what we call bits, qubits and neurons. This is how we will be building future computation systems, okay? both quantum computation and the brain-inspired computation, they will be more like an accelerators. You will still have digital computing core, which will sort of manage the whole show. So that is how this vector is emerging, right? But as I said, this is all fine, in the context of intelligence. We are making these compute and storage systems more and more powerful. But I also want to bring in this notion of smartness. Okay? What is smart nanoelectronics? We are doing intelligent nanoelectronics, but not smart nanoelectronics. Smartness is about being aware of your environment, right? What do I mean by that, right? And adapting to the environment, right? So how do you become aware of your environment? As I said, just compare with yourself. We have our computation engine, which is our brain. But for this brain, we also need all these sensory organs, right? The panchendriyas, as we call, right? Which do all this interface with the external environment. You need sensors and actuators, okay? So we need to really focus on sensor electronics as well. That our efforts have not been as strong as we have put in on computation and storage, right? We need sensors and more sensors, automated machines with ambient intelligence, and that comes when you have sensors, okay? And of course, adaptive control and actions, that comes with actuators, right? We move our arms and control things. That's actuation, right? AI, robotics, IoT, smart factory, what you have, all these new systems, applications that are emerging, that would need smartness as well, along with the intelligence, which comes automatically by computation and storage engines that So, in other words, the systems that you have to build going forward will not only be based on, just what is called Moore's law, or making, these computation and storage components more and more efficient, but also something called more than Moore. We need something more than what Moore advocated, right? Making computation and storage chips more powerful, also adding all your sensors and actuators on the same chip, okay? I'll give you a motivation just so that you understand why we want this, right? You may ask, why do we need this? I want to motivate this with our human olfactory system. Olfaction is sensing smell, right? And of course, that happens through nose, but what happens inside the nose? When you go in, dig deeper, there is an area which is a sensor area inside the nose, which is about 10 centimeters square. It's 3D. It's not 2D like a planar electronics, right? And that's why you can actually have a very compact 3D engine there. And there are 6 million sensors, okay? Biologists call them receptors. But these 6 million sensors give us this amazing, olfaction system. How amazing is it? There was a very detailed analysis that was done, and it was, published in Science, and subsequently Nature magazine picked up the story, and the analysis was that because of this, we can sense 1 trillion odors. Did you ever imagine this? You can differentiate 1 trillion odors. That is how complex and efficient your nose and the olfaction system is, okay? Let me show you this, right? You know that in airport dogs are used, right? Not human beings, right? As sniffers. Why is that? Their olfaction system is even more evolved because they have 300 million sensors as a that point of view. And also, although the dog's brain is smaller, and that's why we say that we are more intelligent, the section of the dog brain which senses smell is actually bigger than the section of our brain which senses smell. And that's obvious, right? If you have 300 million sensors about to 6 million sensors, your back-end computing and inference engine has to be more powerful, right? So that is the kind of system that you have here. You see, you have all this computation and storage which happens in your brain, and you have this sensory system. Only when you couple these two, you will be able to generate these new generation systems which do not exist today, right? So I just wanted to tell you that there are many reasons why we have to focus on this. We have not been doing that, okay? So the future intelligent and smart nanosystems will of course have a lot of computation and storage, which will include bits, qubits and neurons. But in addition, they will also have massively parallel sensory engines, right, all working in unison, and thereby providing you an amazing functionality, which is even hard to imagine for us today. Okay, these will be discoveries which will be coming in the next 2 decades or so. Okay, so that's just the 2 different vectors I touched upon, what is going to happen in computation and storage. And the thing that we have not focused on, which is really building these sensory engines, which come together with this computation and storage and really build this future systems, right, nanoelectronic systems, which will make all this AI and other things possible, right? Okay, let me just quickly get another 5-10 minutes and close. Is that okay? Right. Okay. So 2 examples I'll give you just to tell you that how, when you really integrate the sensors and the electronic computation and storage, what you can achieve. One we call lab on palm. The other one is electronics nose. They will of course use a lot of electronic chips, silicon chips. They will also use what is called printed electronics, okay, and silicon electronics of course. They will also go beyond just the computation and storage. They also do sensing, right. They use what are called oxidation reduction reactions also, okay, and thereby you will be able to get this, right. So I showed you the ENIAC, remember that, computers, how we used to build. So ask this question, how were doctors diagnosing diseases 100 years ago, right? And pathology lab 100 years ago looked like this. You've gone to pathology lab to give blood samples and all that, right? There is no comparison. Just like there is no comparison to the ENIAC computer and your handheld device, okay? Again, in this area, a lot of development has happened on many areas, including electronics and computation. And the biggest transformation happened in 1980s in what is called immunoassays were developed. That's in the context of biology and chemistry, but at the same time electronics and computation tools were also becoming more and more powerful. They came together, and that's how modern pathology labs were born, right? There was development in this area of biology and chemistry. There was development in this area of computation and electronics. Both came together. You go to any pathology lab today, you give the blood, through the window you may have seen the equipment sometimes. All these equipment look like this. These are called autoanalyzers. These are analogous to your desktop computers or your mainframe computers. But today in electronics and computation and communication, we have gone to mobile era. So what next in healthcare, right? So the next in healthcare, what World Health Organization says, you need to provide 3 A's actually. What are the 3 A's? World Health Organization says you need to provide 3 A's actually. What are the 3 A's? Healthcare has to be available to everybody. It has to be accessible. If it is just available, and only if we sort of bring in learning from what has happened in communication and computing into this area as well. So this is what we started thinking about 2 decades ago when I was looking at this area. This, by the way, is a very, very highly interdisciplinary area. I mean, I told you even making chip is highly interdisciplinary, but here it's highly interdisciplinary because there is also some other vectors that are coming in. There's biology involved, there's chemistry involved, in addition to all your electronics, manufacturing and all that, right? So again, you have to start from basic science, you have to have engineering, technology, and eventually thinking about the manufacturing, right? And oftentimes you really have to think out of the box if you really have to innovate, right? So this is an amazing journey that we have gone through in the last 2 decades, from an idea that we started in the early 2000s, started working on this through many research students in IISc with many collaborators also, and we formed a company in 2015 called Pachod Healthcare, because by then we had come up with some very interesting novel technology. We had some 30 international patents in 8 countries. So we thought, rather than just leaving in publication and patents, this is the time really to take the next plunge, right? So that's how it was born. And then, if it is a medical device, it has to really go through a lot of regulatory clearances. And to cut the long story short, today we have a very interesting product which is actually used in more than 15 states as of today in India, right? And it's been used remote corners where even basic facilities are not there. And this is okay. Let me skip some of these things. Right. Many of you have seen glucometers. Almost every family has a diabetic patient today. This is an amazing invention. It started way back in 1960s in a university by Professor Leland Clark. He's often called as the father of biosensor. And then in 70s, the first glucometers came. I mean, if you look at first glucometers, they don't look anywhere close to this. Just like a first computer, right? Huge bulky devices, right? But today you have amazing glucometers, you have these disposable sensor strips, instantaneously you can measure your glucose at home. You don't even have to go to the pathology lab, okay? Now the key element here, of course this is a device you can see, electronic device inside, but an interesting part of this is also this sensor, right? If you don't have this sensor, you cannot build this system. That's what I said, sensor working along with this computation and storage unit. If you dissect this sensor a little more in detail, right, this sensor is actually firstly not made on silicon, it is made on plastic. And we don't use lithography and other processes, we use printing technique. That's what I meant by printed electronics, right? So it looks like your PCB tracks, that you will see. These are printed tracks and there are some electrodes here. This is what is called an electrochemical cell. And in fact, this is what you will see in batteries also, right? What you do in batteries, in electrochemical sensor, it's an opposite, right? In batteries, you apply a potential and create some chemical reactions. In electrochemical sensor, the chemical reactions lead to electrical current. So that's the connection between your electricity and chemistry, okay? So now, if you look at this, an electrical equivalent circuit, engineers always try to look at an equivalent circuit, right? So electric equivalent circuit looks like this. There are 3 electrodes. One of them is called a working electrode and the other one is called a reference electrode, and there is something called a counter electrode. You apply a potential, which is called a oxidation or reduction potential to cause those chemical reactions, right? And then you measure the current. In theory, you could have just done it with 2 electrodes, but there are issues because you don't want to have series drop affecting your potential, and that's why you measure a current through a third terminal, okay? How is glucose sensor made then? So the strip that I showed you, what is done in that strip is that the working electrode is coated with an enzyme. Enzymes are very interesting molecules in biology and chemistry. They essentially react with only certain elements. So this glucose oxidase enzyme is very sensitive to glucose, right? Because if you're doing glucose sensing, you don't want to also do a hemoglobin sensing, right? It should only better do glucose sensing only. You don't want any interference, right? So this is what happens in this sensor today. You have a working electrode, this is coated with what is called an appropriate sensing chemistry. That's where the magic is, right? And that's where you have a glucose oxidase enzyme. So it ensures that the only glucose will have transport to the working electrode. But this is a very sluggish reaction. In electronics, you use what are called amplifiers to enhance signals. Similarly, here also we use what is called mediators. These are not called amplifiers, but they are effectively doing a job of an amplifier. There's what is called a ferrocyanide mediator, and it's essentially enhancing this electron transport. So you apply a potential which is equal to redox potential for reaction with glucose. Glucose oxidase ensures that it is only glucose that will react, and this mediator will enhance the electron transport, and you have a current that is measured, right? If you have more glucose, you measure more current, right? That's how your glucose sensor is made, right? And these glucose sensors are all available today. But what we thought back then 2 decades ago is that glucose is okay, but you need to go beyond glucose. Just in diabetes itself, forget about others like you heard anemia, malnutrition and other major health issues. In diabetes itself, HbA1c is a gold standard today. Glucose is not what doctors go by, right? Now, can you think of a device which can do all of this, right? So that is how we started this journey, and today we have this device, which can do 8 different tests on a single device. Each of these tests has a different sensing chemistry, right? As I said, that's where the magic is, right? And you will have to insert an appropriate, strip, and then you can do glucose. Of course, you can do HbA1c, which gives you a 3 months average glucose level in our body, right? So this is perhaps the first point of care HbA1c device, right? And there are other interesting tests that you can do also, right? And also a very interesting thing happened during COVID pandemic. The government knew that we had already this device which we had for so-called non-communicable diseases. They asked, can you do something for COVID also now, right? So, we started working on it in the middle of the pandemic. It was very, very hard. It was hard to even go to the lab, right? So, only because we got a certificate that we are working on COVID technology, we could do this work. So this is an amazing thing that happened in just 8 months. We started from a very interesting new idea. This is different from the COVID tests that you have seen in the market, which are like pregnancy tests, right? It's a cartridge that you put your blood, it gives a color, but that's only qualitative. For quantitative COVID antibody tests, you have to go to pathology lab. So what we have been able to do actually is do a quantitative test at point of care, right? So we started with an idea, and we went through all proof of concept, field validation, and certification also, because all these require very, very stringent ICMR and CDSCO certification, right? All this happened in less than a year, right? This was an amazing thing that we could go through, because we had built that expertise, on working on this technology, and it's just showing some demonstration. You will see in a while the result will come, which also gives you a quantitative information. But let's move on. And as I said, it's this technology is in use in very, very remote areas, where ASHA workers are taking this device, rather than these people going to a nearby taluk headquarter or district headquarter. This is happening at point of care, right? You can do the test instantaneously, and many example use cases that are out there, right? So that is one example. I showed you what happens if the sensor technology can fuse with the computation and storage, right? So very quickly, this is still work in progress. Can we build there's a lot of electronic nodes work happening, but it's at different level. But on a single chip, can we do everything, right? So that's the holy grail. We still don't have that technology today, but this is a technology that we are working on. Again, this is still not a product. We hope that this will also become a product, just like a healthcare product I showed you in a while ago. This is what is called a chemi-resistive sensing technology, right? You have a sensor again. The sensor gives a current which is proportional to your concentration of your ambient gas, okay? And then you have your front-end electronics, which amplifies the signal and makes sense out of the current that you're measuring. Today, what we have been able to do is we have been able to generate a wafer scale technology. Each chip that you see here is an array of 4 sensors, right? Nowhere comparable to the 6 million sensors of human being, or a 300 million sensor of a dog's olfactory system, but these are baby steps, right? So each of the 4 elements is functionalized with a different material, so that one of these can sense carbon monoxide, carbon dioxide, sulfur dioxide, and NO2, right? And eventually we want to have hundreds or thousands of sensors on a single chip, right? So that is the eventual goal, and we are also working with many. Even this sensor products can be made. This is a product that we are working with ISRO. They are actually using this for their launch vehicle site, detection of hazardous gases, right? But what we really want to do eventually, on a single chip, you have all your electronics done on the chip, and on the back end you should be able to put these sensors all all these sensors at a very large scale, and your sensing, computation and inference all happen on a single device, right? Again, we have been able to show a 30 sensor element array here in this work, right? But this has to scale as well. We have gone from 4 to 30, which is an order of magnitude, but again, we have to go to hundreds, thousands and so on and so forth, right? So that is where there's a lot of work that's happening. I'll skip some of those things. So eventually the way to build these electronic nodes, again you will have your computation and inference engine, which is on silicon. It could be using not just digital bits, also the brain inspired neurons, equivalent circuits, and then you will have all your analog front end and sensing materials, all on a single chip. If you can do, then you will have a nose on a chip, right? So that is an ultimate thing that you can realize, right? So we are nowhere near that, but hopefully in the next 10 years. Okay, thank you. Yeah. Yes, please.
So the glucometer, what will be the order of currents and how are we measuring that small current related to glucose level?
Yeah, the order of currents are in microamperes, okay, and it's not difficult to use microampere current. This all on packaged system, right? So because if you have it in open ambient, then you will be picking up. We are surrounded with lot of RF noise, right? There are things that you need to manage, but microamperes is not a difficult thing. We have also done nanoampere kind of current measurement. It's doable. Yeah. So just on the glucometer question, that by the way, the device that I showed you right now is for healthcare practitioners, but we will be bringing out a device soon even for home diagnostic. But right now it's what is called a B2B segment. That is, doctors and practitioners are the one that are using. This glucose sensors also need very stringent criteria. And in India, if you want to sell glucometers, there is a lab in Delhi called National Institute of Biologicals. You need to get it tested by them, and they have a lot of statistical measure. And something that they said, which was very heartening, is that they, for any glucometer, even which comes from abroad, like Roche or Abbott, they all have to first go through that lab. And then they said the kind of accuracy they got with our sensor beats all of them, right?
Is there an opportunity for any of the interested, maybe one or two, to work on any projects like that, sir? Is there
Well, if you're asking whether they can do their BTech project, I think that becomes very difficult, Yeah. Yeah, any questions? Yeah, no question is a dumb question, right? So yeah.
You spoke a lot about the research that is done on electronics to mimic the sensory organ of the nose. So how close are we to building it, and what is the current scenario? Like, what is the biggest hurdle that we are facing in realizing it?
Yeah. I mean, as I said, we are not really anywhere close to that. The biggest hurdle is really to, even the understanding of our. See, when I say brain-inspired computing, now we have understood a lot of things on how brain works, because there has been a lot of work that has. So now we are trying to really mimic, by having these brain-inspired building blocks. But our olfaction system, we are still trying to understand. how does it work really? When I say 6 million sensors, are they all different, or is there a redundancy? Are there a few set of different sensors and the redundancy is built in? And how does it really work? There's a lot of work that has to happen. Once we get better and better understanding, then the next challenge is how to mimic it, right? It works in human beings, all right, but can I mimic it? Then that is the next question. There are a lot of unknowns there, right? That is a challenge.
So one more question I had was, you showed a quantum qubit. So currently there is a lot of research that is happening in quantum computing. And you showed an image of the brain. So if the transistor is digital, which is 1 and 0, and quantum is basically a superposition of 1 and 0, and we calculate the probability. So then can we mimic the actual brain structure in a quantum machine?
No, again, as I said, these are three different things. We should not mix them up, right? The quantum computation, the advantage of that is really to look at some very complex problem, such as estimating probabilities, and there are many problems that are really made for quantum computation, right? But whereas the pattern matching kind of problem, right, that is not a nice problem for a quantum computing algorithm. And besides, one of the biggest problem today in quantum computation is that all that has to be done at extremely low temperature. Even if you build a 100 qubit quantum computer, you will need a big cryostat to cool it down to liquid helium temperature or even below that, right? So that's a big problem. One of the biggest problem in quantum computation era is, can I build a quantum computer which operates at room temperature? That's an open question. Until we solve that, you can still do all quantum computers, but it will be for demonstration, right? Not for mainstream application.
Yes, sir. There had been few breakthroughs of superconductivity at room temperature also in the past recent years. So that also contributes to that.
Yeah. That's again an area. There have been breakthroughs and breakthroughs in superconductivity, right? Some. So I don't want to talk about it, but yeah, these are very hard problems. It's not that we shouldn't work on it. We should continue to work on it. But there are no easy solutions. These are not low-hanging fruits. Right?
Just one last question, sir. I am an aspiring engineering graduate who has a passion for electronics. So if I want to get into electronics or do more research on it, so what would be the path that I need to follow, or any guidance that you?
Yeah. See, to pursue your interest in an area, there is no hurdle really. It's only mental block, right? For example, I'm an electronics engineer. I could venture into it, and my student who is actually driving that company now is an electronics engineer. And converse is also true. Intel was co-founded by a chemistry PhD, right? Moore is right. So the point is that if you really want to do that, you should be able to pick it up anytime. Okay.
Thank you, sir.
Yeah.
Hello, sir. You're talking about the human brain interfacing to the system. So what are the hardships we're facing right now in regarding to give our conscience to the system?
No, I'm not even talking about conscience. That's that's a too complicated problem. But even before that, right, computation, we are already doing neural networks, but that's all done in software today. The next thing, IBM came up with this chip called IBM True North. Now they try to move that software onto chip, but that's using transistors. But transistor is not a good analogy for a neuron. Neuron is a very interesting element. It does summation and it does thresholding function, right? So that is our building block, unlike transistor. So the next thing that people are trying to do is, can I do an electronic element which is not transistor, which looks like a neuron? So that will be the next thing. And those elements are called memristors, right? And people have demonstrated that. Now the question then is, how will you, yeah, memristor is a very interesting element. It's actually called a fourth element. Often it's also called a missing element, right? You know, you have a resistor, inductor, and capacitor. Almost 30 years ago, a professor in UC Berkeley said there should be a fourth element. We say that 3 is not a good number, right? So he said there should be a fourth element, and that was called a missing element. He theoretically proposed that this element should be there, and that element was later discovered as a memristor, right? So we have built that now. Now the next question is, can we build it at scale and then mimic a neuronal circuit? If we can do that, then we can move all the AI and inferencing. We have been doing amazing things, natural language processing today, ChatGPT. All this is amazing AI, but that's all happening at software level, remember. Right? While it's giving amazing performance, the power consumption is just unimaginable. Right? So we need to move it to hardware and eventually brain-like building blocks. That's what I mean. Consciousness, let's not talk about that.
So apart from consciousness, can we access the operations what we are thinking in a brain?
No, I think let's not get into that. Yeah.
Okay, sir.
Yeah.
Thank you.
Good morning, sir.
Yeah.
As you mentioned about the electronic nose, and we may reach its maximum functionality in a decade or so, where exactly we use that in our future?
Pardon me?
Where exactly we use that electronic nose technology you mentioned?
It could be anywhere. It could be anywhere. You know, you may be going around. You know, there may be, it's an interesting times we are going through. While we are making all this progress, there are also a lot of threats. You don't know whether a bomb is sitting next to you. You may be carrying an electronic nose which tells you there's a bomb here. What I'm saying is that it's unimaginable possibilities, right? Yeah, exactly.
Thank you, sir.
Yeah. Okay. Yeah.
Yeah, thank you very much, Dr. Navakanta Bhat. Navakanta Bhat, in a way, he's my classmate, but I'm senior to him. Okay, so at IIT Bombay, so we were together. And when we wanted to request Dr. Navakanta Bhat to give this lecture, that time he was in the US. And we were really doubtful whether he can make it. Then he told, without taking even a minute more, and he told that he's going to come, and he's here today. This particular conference, as you know, this is on smart technologies and also on innovative technologies. I think what could be that lecture which is going to parallel with Navakanta Bhat's lecture, which is going to be relevant to this particular topic. I think it was a wonderful lecture, Dr. Navakant. So thank you very much for taking your time and then coming over here. I think it has inspired all of our participants and especially our students. And I think now I think you must have come to know that in electronics there is no end for the research. Every time when you think of something, there is something which is going to happen tomorrow. There is something different. I think he mentioned that whatever the electronics things that you are going to buy, you should not buy it today. I think you should buy it for tomorrow. And I used to tell it jokingly. I think 2 things you should not hurry up in your life. One is to get married early, and the other one is to buy mobile early. In both of the cases, later you'll repent to that. If you had waited for some more time, you would have got a better model. Okay. So anyway, thank you very much, Dr. Navakant. And it was a wonderful lecture. And we are hoping that BNMIT Research Center in Electronics, and we have established a Center of Excellence in Healthcare. We are going to collaborate with you people, and whatever the kind of research that could be done here, we can also carry out with that. So thank you very much for your time. Yeah, thanks a lot. Yes. I think I should tell that. IISc has developed a nano electronics fab lab. Okay, so it is wonderful to see. I think it must be.
You're welcome to see. In fact, every Friday afternoon is an open day
for
us,
Hmm.
and a lot of students come from many colleges.
Yes. It is wonderful to see. This clean rooms and all the fab facilities which are being developed. I think it is one of its kind, and it is not there anywhere. And fortunately, we are in Bangalore, and this is at IISc. I think we can make the plan for that. I think Aisha madam, take electronics students. Yeah, Okay, thank you.
Okay, thank you.
Yeah.